Okay, so good morning, and let's proceed with our discussion on the adders, right? So yesterday we looked at the mirror adder, right? And where we sort of applied all the concepts that we learned in module 4 in order to design this adder very effectively. Okay, and what were the things that we did? We used the mirror principle, right? Mirror idea to reduce PMOS stack size, right? Then we assigned the carry, which is the timing critical signal, right? C in, which is timing critical, to transistor of least logical effort, right? Then it also so happened that the transistor with least logical effort was the transistor that was connected closest to the output. So C in, right, connected to transistor closest to output, right? And then we optimized some circuit to be generated from Cout or Cout bar, right? Otherwise the 3-input XOR implementation is going to be very complex. Instead of that, we were able to reuse the Cout bar. And why was that okay? Because we showed that in the ripple adder, the Cout is actually the signal that's on the critical path. Only for the last adder, the sum is on the critical path, right? So if you remember that, we said that when I cascade full adders like this in a ripple adder form, right? So this is my C in, A0, B0, S0, A n minus 2, B n minus 2, S n minus 2, S n minus 1, again A n minus 1, B n minus 1, and this is Sn. So it turns out that only for the last adder is the sum actually going to be on the critical path. For all the remaining n minus 1 adders on that ripple chain, it's a carry out that's going to be on the critical path, right? So this is the critical path. So if I want to optimize this path, then I have to make sure that the carry out is fast, the sum can be slow, and that's what we saw when we wrote out the delay expression, right? Ripple adder, we said, was T sum for the last guy plus n minus 1 into T carry, right? And that's why we chose to optimize T carry so much rather than sum. Okay, so with this we got a very nice circuit implementation in static CMOS logic, right? That you could have good drive strength and all that stuff, so there's no problem. Today we will see a few more maybe alternate circuit implementations. Okay, just briefly, I'm not going to go into the details. I'll just show you the circuit, maybe a quick analysis, and I'll just tell you what the key advantage of that circuit is, right? So before we go into that, let us also figure out, when we mark this critical path, in what mode should each of the n adders be in? Should it be in generate, propagate, or delete mode? Okay. So let's start with the bit 0. Should it be in generate or propagate or delete mode? Should it be in delete mode? What does delete mode mean? It means the carry out will be set to 0. Doesn't matter what the Cin is. Will that be the worst case? Huh? No. Right? So what mode should it be? Yeah. Propagate, or it could also be in generate, because both to propagate Cin it's going to take 1 unit of time. To generate the carry also it's going to take 1 unit of time. So it really does not matter there. So this I would say can be in G or P mode. No problem. What about the other n-2 adders? N-1 adders actually. Everything has to be in propagate mode. Okay, this is important because when we go to the other architectures of adders, this thing will slightly change. You have to be very careful. Once you carefully identify which adder is in which mode, then it's very easy to figure out the critical path. Okay. So what we are trying to do is, for the worst case delay, what mode of operation should each adder be in? This is what you have to first identify. Then it's very trivial to write out the expression for the delay. Okay? Yeah. It could be generate, because see, generate is, let's say the carry is being generated or the carry is being propagated. Both of them take 1 unit of time. See, to generate, you have to do that A and B operation, right? That's a logic gate. The carry propagate is also like an AND gate, right? So maybe since you asked, so what was the expression for propagate? A XOR B. Generate AB. Now can you write the sum and carry in terms of this? In terms of P, C and G. The sum is what? P XOR C, correct? A XOR B XOR C in. A XOR B is P, therefore it's P XOR C in. What about carry out? Yes. Either the carry is going to be propagated, which is controlled by the signal P, or it will be generated. The delete you don't have to take care, because delete is the case when both P and propagate are P and G are 0. Output will automatically be 0. So this is nothing but G plus P into C. So to answer your question, basically for the C out to be ready, either you have to do this operation P into C in, or you have to do this operation. Right now we are saying, assuming these two operations are of similar time, it doesn't matter if it's generate or propagate. Of course, generation of P itself is an A XOR B operation. Then you have to do the AND with C in. So technically that will take slightly longer. But assuming these two delays are reasonably comparable, it's okay, G or P is what I'm saying. Otherwise, it's fine to even say that this has to be P. Right? But the others cannot be in generate mode. That's all I'm saying. Okay? So it turns out that we can do one more optimization, to this. So if you remember yesterday, we said that, we wrote out the mirror adder circuit, right? Let me just write that here. This is basically the pull down network. This is the mirror pull up network. This gave me C out bar. Then we said you have to put an inverter here and get C out. Now similarly we did something for the sum. Right, we had a pull down network for sum and mirror pull up network for sum. This is C out. And we got S bar and we had to generate S. Now look at what happens when I cascade these things. Okay, this is a full adder. I'm going to put it in a ripple form. Okay. So what is happening is, in order to generate C out here, I have to go through that extra inverter, right? And then feed it into my next inverter. So if you look at the number of inverters on this path, you're going to have one inverter per full adder, right? So you're effectively adding n more inverters on the path, and you're going to increase the delay. Okay, the difference, remember, is because this is like an array structure, I cannot do gate sizing like algorithm where I make this full adder very small, next full adder large, and I can't go like that. It's better to have a nice array structure, especially when you go to multipliers and all that. It's better to keep the layout same. So it's effectively the same full adder that will get repeated. So it's not like I can use those inverters as buffers and speed up that path. It's the same inverter, right? So effectively, I am going to add n inverters into this path. Okay? And the problem is that is going to increase my delay. What I want to do is, I want to get rid of this completely, right? Or at least it's okay. I don't mind the sum part. I want to get rid of the carry out delay, because that is what is going to go up as n minus 1 times delay on the critical path, right? So question is, how do I eliminate this? Any suggestions? You use the complement idea, in the sense we already know that the mirror property was used here, because if you complemented the inputs, the output of this full adder will also complement itself, right? So we said that S is equal to f of A, B, C. S bar is equal to basically f of A bar, B bar, C bar. That's why we could do this mirroring technique in the first place. So which means that if I want to give the complement inputs, all I have to do is I have to complement all the inputs, then the output will also get complemented, no problem, right? So what you have to do here is, the first thing, you make another full adder block FA prime, which is basically the full adder without those two inverters. Okay, no inverters there. You put inverters later to get this sum S0. Now this is my C in. So I leave this as A0, B0. Okay, I have removed the inverter now. So what do I get here? C out bar. Now if C out bar is going to the next ripple adder, what should the other inputs be? Exactly, right? A1 bar, B1 bar. What will you get here? You will now get S correctly, because I have removed the inverter from that. FA prime is this circuit without those two inverters. So you will get S1. What about the carry out? Again, it is just C out, right? So the next stage, you can basically put a FA prime again, give the right inputs, A2, B2. And what you will get here, again you have to invert S2. And you do this. Yeah. That's a very good question. So the point is, yes, for A1, B1 and all that, I am using another inverter and increasing the delay. But remember that all these signals arrive together. So every alternate stage I'm going to invert. All those inversions happen in one shot. So if you look at the arrival time of these signals, this will arrive at 0. This will arrive at 1. This will arrive at 0. The next A3, B3 will also arrive at 1. So in some sense, by the time this full adder has evaluated and propagated the carry, this guy has already inverted the inputs. Clear? So this is another technique which you can use in order to optimize the delay, and it is very useful in specifically in the multipliers. I'll show you that when we come there. Clear? Any questions here? Okay, so with that we have done a lot of optimization. How many transistors were there, by the way, in this full adder circuit that we made? Yeah? Totally how many transistors? In the mirror, in the pull down network of the carry out, there were how many transistors? 5. Right? So I'll put that 5 transistors here, 5 NMOS. Here, therefore, this is also 5 PMOS. What about the sum? 7 NMOS, 7 PMOS. Assuming that I also had to generate the the actual Cout and sum, I would need 1 NMOS here, 1 PMOS here, 1 NMOS here, 1 PMOS here. So total number of transistors is how many? 14 plus 10 plus 4, right? 28 transistors. And by the way, earlier I also, when I gave you the assignment, I asked you to do the carry out with the carry out circuit upsized a little bit. The reason for that is again what I just told you. The full adder is just repeated n times. It is not a thing. So if I have all unit size devices with this load, it may not be able to drive it. So it's not that I can optimize that sizing and then figure out what the correct sizing is. So as a thumb rule, you upsize it up by a factor of 3 or 4 and then repeat that adder, your delay will be okay. This is an empirical thing that has been found and it reasonably works. That's why I asked you to upsize the carry out circuit alone. Some I don't have to do it because it appears only once in the critical path delay term. So the sum is left as a regular circuit, in the sense the sizing is just the usual sizing that we get. Okay.